Grün.
No. The green button?
Ja.
Okay, here we go. Okay, hello everybody. So today we would like to introduce you to ICU topics. So I'm the head of R&D at ADVITOS GmbH, and we are focused on extracorporeal blood purification. But compared to standard therapies, we have a bit a different approach for therapy, and we think a bit bigger for the therapy. And why? I will tell you within the next slides. So what is the current situation and the problem on the ICU? So what most people don't know, that about 60% of all death people on the ICU are caused by multi-organ failure. So in numbers, that means about 500,000 people die each year in Western Europe and the United States alone, suffering from multi-organ failure. Sorry. But what is multi-organ failure? So we have lots of different detoxification organs. And here on the left side are shown our three main detoxification organs. And when you get incorporated on the ICU, intensive care unit, you get a so-called SOFA score rating. And that is a number that shows how high the mortality risk is for each patient. And that is here shown in percentage. So if you have a single organ failure, like kidneys or lungs, then about 20% of the people incorporated on the ICU might die. And if you have a multi-organ failure, so for example, lungs and kidneys fail, it's getting up to 50%, and then it's increasing even more to above 75%. And that vicious circle is due to side effects of each organ within your body. So that's what you can see here on the right side. These three organs are responsible for the detoxification of H+ ions. So they produce a good blood pH in your body. And if one of these organs is failing or is starting to fail, then you have negative side effects on the other organs of your body. So it's very, very important that you do not look at just one single organ. You have to take a look at all the organs and their side effects. Here you can see how this treatment is taking place today on the ICU. So on the side here, you have standard therapy device for kidney support. Here you have a device for kidney support with a combined liver support device. Here you have a breathing machine for lung support. You have several drug delivery, infusion pumps, and all that stuff. So the problem on the ICU is that all these devices have their own software, their own algorithm, and there is no communication between all these devices. The only communication between these devices is over the patient's body, and then they could have negative side effects on each other, or you have to have a doctor with such a huge brain to combine all these parameters you could influence, because each of these devices has a bunch of several parameters you could influence for the treatment. And in addition, you have continuous blood gas monitoring and different other sensors connected to the patient. So you get a lot of information from the clinical data system, and all these values have to be combined so that you know how to treat the patient. And that's the point where ADVITOS started. So we invented a device to treat for all these four organs. So with this holistic treatment approach, we increased the patient's risk because the invasivity of this device is reduced dramatically. And that could also be shown here on the right side. On the above place, you can see with standard care today on the ICU in this trial study, the survival rate of all these patients was just 16%. Compared to the therapy with these 4-in-1 device, the survival rate was increased to above 40%. And now the question is, why should we use AI in such an environment and in such a treatment? So what I already started is that we have a bunch of clinical data. And as you have seen on this picture before, the combination of all these data is really challenging. And it's also time critical because you have to act very quick on the ICU, because this vicious circle could get quite quick, that you have negative influences on different treatment approaches for the patient. Then we have a huge data pool of informations, and that is also a combination with clinical informations, with different drugs you get for the patient and all this stuff. And that's where we start with our AI model. So together with Fraunhofer Institute, we decided to develop an AI model where we get all these informations incorporated, and in addition, we got some human inputs to improve all these informations and model, because it's quite complex. It's not just one single value for these ICU patients you should influence that you get a positive treatment approach. It's a huge combination of different values. And what is the goal of this model? So on the one side, our nurse could define a stage where the patient should go within the next minutes or within the next hours. And then our model could simulate how the patient will change within the next hour or within the next 24 hours. And then we get feedback, how should we change the treatment parameters for this dedicated patient so that we will reach the simulated situation for this patient. And in addition, it's very important or beneficial for our treatment, as we have a completely different treatment approach compared to the standard devices, which are well known for several years. So like breathing machines, standard parameters you can adjust. Dialysis devices, standard parameters, everybody knows how to adjust. But for our device with this holistic treatment approach, you can change bicarbonate solutions, blood pH, dialysis pH. So you have a bunch of different parameters you can adjust, and you have to combine them with the complex patient situation. And here our model helps a lot to give the doctors information how the treatment could go on and how these parameters should be influenced so that we have a positive result for our patient. At that point, I'd like to hand over.
Thanks. Okay, good. So I will now talk more about the actual algorithmic interpretation of this problem, what decisions we made, what analysis we took, and talk a bit about explainability and advantages. So this is the whole problem that we have, and we now looked at a smaller sub-problem. So we have a very nice data set which was actually gathered in the lab by ADVITOS in Munich, and instead of a real patient we have a bucket of blood here. The goal was to reduce the CO2 in the bucket of blood, and in total we had about 21 5-hour experiments of data, meaning that we have about 750 samples, and usually it worked as follows. So we had some setting on the machine, and over some time the setting on the machine now affected the patient or the blood bucket, right? Then this blood bucket, some parameters changed, for instance the pH value or the bicarbonate value, and after this measurement we could then now reset the settings, specify some new ones, and this is basically how our data was gathered. It was gathered on a 10-minute frequency for sampling, and in our data file we had a 17-dimensional representation of this machine, which is now very, very small in comparison to the actual parameters that we had, and we represented the patient as a 9-dimensional vector. This is basically just the blood measurements that we had in our data. And because here the experiment was very much planned in advance, and it was very much pre-described what will happen during the experiment, and therefore we can somehow also say that in this lab environment we can actually argue for some causal relationships and give some intuition about the inner workings, what parameters affect actually. Yeah. And for this problem, we used a reinforcement learning algorithm. And this reinforcement learning algorithm has a very, very similar shape to how we actually gather the data, right? So this algorithm usually selects an action, then it observes a state, and after some time, it sets a new action. All this with the goal to reduce either reduce or maximize a long-term reward. Here we just wanted to increase the overall patient status, or in our case, it is a composite function of the blood parameters that we had. So for our choice, we used a so-called Q-learning approach, which is an offline reinforcement learning method, because we just had observational data. We did not have the chance to actively interfere with the machine live, but we had some recorded data and worked with this data. Now, there are a couple of desirable functions of this reinforcement learning algorithm. And the first one that we had was, for instance, a very stable patient treatment. So a very stable patient treatment is important because the patient, by definition, if he's in the ICU, is very sick. And therefore, we just don't want to overburden the patient with rapid changes in the ADVOS machine. Therefore, we aimed also to have a stable patient treatment, do not change very rapidly. And this is what we can see here on the right-hand side. This was the difference between predictions of the RL algorithm's actions that we had over time. These colored lines are the different experiments that we have, and we see that this is very stable, quite low. On the left-hand side, we can see the actual realized actions that were taken in the lab. This now is a bit misleading, I have to say, because there's a warm-up stage, and sometimes they had their plan how an experiment would look like, and then something happened. For instance, the CO2 was non-recoverable, and therefore they decided just to try out things, try out settings, and this is what we see on the left-hand side. On the right-hand side, what we can imagine that this reinforcement learning algorithm actually picked up some informative plan how to treat the patient over a longer time, which is very nice. And now we also wanted to check whether there is some explainability, whether we can tell the doctors and convince them that this is a good idea to listen to our recommendations. And for instance, what we did here is, now where's the pointer? Here. So if we have a certain patient which looks as follows, and we marginally change just one aspect of the blood measurement, for instance, your blood measurement 2 to 3, 4, and 5, then we could feed this into our algorithm and check what would the action in, let's say, the first dimension of our algorithm be. Meaning that if we would have a different blood value, how different would the RL algorithm suggest that we treat the patient? And here we see the different settings and the different trajectories of the settings of the ADVOS machine. So we see some settings should be aligned. They should be, for instance, increased together. Some should be decreased if the blood measurement would be different. Some would be stable, right? And similarly, what we can do is we can also look on the actual goodness of a patient if we would change one particular blood measurement. Meaning that if we, for instance, would artificially correct the pH value of the patient, would this now be a healthier patient or a more sicker patient? And the RL algorithm does not only suggest actions, but it also suggests how healthy a patient is. And this is here in this value column that we have right here. So we can also assess this. And now based on the slope, this is the slope, right? If we alter different blood parameters, we can sort our blood measurements, which are the most crucial ones to address at a certain point in time. And we know how to address this by the last slide, right? And to sum up the learnings that we have, so now all our analysis, and this is also why I did not show some axis labels, Our analysis is valid for this laboratory environment, right? But if we want to actually conclude statements, clinically relevant statements, then we have to go into real patient data, go into the ICU. This is a lot more messy data. This is more work for me and my team, but this is in the future plan. Also, explainability is very crucial for these domains, especially in medicine. If we don't have explainability, it is a risky domain, and we have to convince doctors, for instance, to trust this. And also, we want to treat patients good. And because we just had a very small sample size, now the transition to active learning would be very beneficial. Active learning meaning that we suggest actions to the ADVOS machine in real time and get the feedback. And although this might not be we might not be able to implement this right now in the ICU, we can still have a small scale enrollment of this procedure. We can start with marginally some small recommendations and have the doctors in the background check this all the time and then extend this. Then there is a new version of the ADVOS machine, and Christoph and his team, they will show this on the DV24 in December. And that's about it from our side. Thank you very much.
Thank you.
Yeah.